Yes, so it is my pleasure to introduce Dr. Eric Burns. He's going to tell us about some things I've been wanting to learn about for a while. So this is a topic that I mostly picked to satisfy myself, and I hope that you will all enjoy it, because just in the past year or so, we've seen the two brightest gamma ray bursts that we've ever seen, and people have been looking at gamma ray bursts since the 1970s. So we call them, instead of the goats, because they're not the greatest, they're the brightest of all time, so they're the boats. And I think on the next slide, we have some more information. Yes. So Dr. Burns is from Louisiana State University, and his work focuses on understanding stellar death and the formation of black holes. He's currently leading the Interplanetary Network of Gamma Ray Monitors, which is very important, especially because when you see really bright ones, it's hard to detect them with the satellites, because the satellites are tuned to look at really faint ones and they saturate, but I'm sure he'll tell us about that. And his discoveries and the discoveries of Fermi and Swift and other satellites that have been studying these bursts have been featured on all sorts of media channels. So now we get to have our own up close and personal look at these boats. So take it away, Dr. Burns. And I guess we switched the screen sharing now. All right, that's good.
I think I have everything set. Okay, so thanks to Lynn and Ariana for the invitation and the nice introduction. I am in Louisiana. It got up to 65 today, so I don't quite have the cold that the rest of you seem to be dealing with, but we will eventually get there in a few weeks. And I think this is a great group. I wish something like this existed when I was in high school, which was a longer time ago than I care to admit. But I'm excited to be here to talk about gamma ray bursts, which I study, and as Lynn said, two particularly interesting ones. So this is an all sky image of the night sky. You have along the center, the plane of the Milky Way, the galaxy that we live in. You can see the small and the large Magellanic Clouds. And then these dark regions are dust in the Milky Way, pieces that haven't condensed down into stars yet. And this image is taken in optical light, also known as visible light. If you had a particularly dark sky, you could see some of this, but not all of it. This being most closely related to the wavelengths that you yourself can see. But the full electromagnetic spectrum, the full range of light that we have is much broader. If we go down to lower energies, you have infrared. So you can still make out the Milky Way, but it looks a little bit different. You lose some detail in certain areas, you gain some detail in additional areas. And this is kind of most closely related to heat vision. So if you could see infrared light, you actually couldn't see much at all because you would blind yourself from your own body temperature. The lowest frequencies are radio. This is an image from the Planck satellite. Again, the nice flat Milky Way comes out, but now you see much larger extensions above and below. These are gas that has kind of spread out around our Milky Way that really only appear down at these particularly low energies. And this is most familiar for Wi-Fi, which is what I'm using to talk to you at the moment. If instead we go to higher energies above optical light, you get into ultraviolet. These black regions are not, blank regions on the sky. These are just limitations of the detectors that we've had to make this image. Those are regions that are too bright to really study in detail, but you can still see the brightest regions, the Milky Way, and you can see, it looks kind of like optical. You have to worry, or many of you have to worry about this for sunscreen. On a sunny day, you want to make sure you don't get burned. So sunscreen protects you from the ultraviolet radiation that survives through the atmosphere down to the ground on Earth. If we go even higher, up into X-rays, the sky begins to look quite different. The Milky Way is still obvious. The dust lanes come out, but now you see an enormous amount of little points scattered all around. These are other galaxies emitting in X-rays, and also these large regions coming out from the galactic center. And X-rays, you know from X-rays, the older but still used technology to look at bones inside of bodies. And the last one I have for you, the highest energies are gamma rays. These are the ones that I study. You have the Milky Way coming out, nice and gorgeous, little points of light from other galaxies that have active black holes. In gamma rays, we don't really have analogs that you encounter particularly often. So the most relatable point is that they turned Bruce Banner into the Incredible Hulk. And using all of this information together, we can study the sky across the whole range of photon energies, from radio all the way up to gamma rays. And in doing so, we can learn more about the universe than we get only from optical or only from radio information. As the name might suggest, gamma ray bursts are most famously studied in gamma rays. And the founding of the field was actually something of an accident. So in 1963, the US, the UK, in the Soviet Union, we were in the Cold War. They signed the Partial Nuclear Test Ban Treaty, banning the testing of nuclear weapons outside of being underground. You can't do them in the atmosphere, you can't do them in water. And you can see now the modern signatories being most of the planet. But to make sure that the Soviets were actually following this, that they were not testing nuclear detonations, the United States launched the Vela series of satellites. So this is, on the right side, this is a person for scale. The satellites are quite large, and you can see at these vertex points, a bunch of little cylinders. These are your gamma ray detectors. And they have, they were launched because, so someone knows, when nuclear bombs detonate in the atmosphere, they release gamma rays. So if you have Earth, you launch a pair of Vela satellites on either side. If a nuke goes off anywhere on Earth, we will know for sure if it's in the atmosphere. And that this light curve on the left, so as a function of time, you get a very brief sharp flash, and then a longer lived decaying tail. It's a really smoking gun signature of a nuclear detonation. And as Zach has pointed out, we found one of these. It's known as the Vela incident. There's been a single atmospheric nuclear detonation since the launch of the Vela satellites in 1963. So they have served their main purpose at least one time. Instead of seeing many nukes, they saw what are now known as gamma ray bursts. And again, you have your light curve, a measurement of count rate over time, having very low from your background, and then these bursts of gamma rays that are short-lived. They were first detected in 1967 and first announced just over 50 years ago. Their discovery was effectively unexpected. It took them several years to be certain that they were coming from outside of the solar system. It's commonly said that they were classified, but that's not true. The lead author, Klebs et al., just didn't actually know how to write a scientific paper. He was not a scientist, so it took him 2 years to figure out how to do that. But this is the founding of gamma ray astrophysics. We've advanced our understanding a lot over the past 50 years. And this is a representation of what we think is happening. So you have on the left in the center a black hole. It has an accretion disk that it's eating and using to drive the expansion of these jets. Shells in the jets collide with each other. That collision powers the prompt gamma ray burst signature, those light curves that I showed you. But afterwards, so here you have your internal collision. Afterwards, the jets keep going. You have this aftermath of this explosion that you can continue viewing, in some cases for years. So I find gamma ray bursts quite interesting. I think they hold a number of records. If you were looking at the right spot at the right time, you could have seen one of these from half the universe away with your own eye. That's the record by a factor of about 10,000. They're the most luminous electromagnetic events since the Big Bang itself. They're the first event seen in light and gravity, and the brightest and the second brightest of all time. I'll discuss in a little bit. And one question we often get when we talk about these is, can they affect us? And the first major mass extinction in history, some people have argued could have been caused by a gamma ray burst. It's not proven, it's maybe speculative, but it is something that's possible. So when we study these events, we classify them. There are short ones and there are long ones. On the left, you can see a histogram, a distribution of how often we see bursts for a given duration. So you can see there's a population of short bursts being under about a second long, and a population of long bursts being about 100 seconds long. And if you look on the right, you see these light curves. This is how we usually study these. And this one, if you look at the bottom for their time scale, this one on the right and the bottom left are all short. They're under about 2 seconds. And the other three are much longer. So those three are all long gamma ray bursts. If you can look at this and you can do this, then you can do a reasonable part of my job, which is just classifying gamma ray bursts. So with really in the past maybe 20 or 25 years, so only kind of the second half of the study of these, have we begun to understand where these come from. So short gamma ray bursts, these are the ones that I studied first when I was in graduate school. On the left, you have a representation of the physical scales in size comparison of Earth, where we are, Jupiter, our largest planet, and the sun being the largest thing around. If you take the full mass of the sun and you crush it down to the size of a typical city. So on the right, this is Baton Rouge. At the moment, I am right about here. But Baton Rouge is a city of about 1 million people. If you take the full mass of the sun, you crush it down into the size of a city, that's a neutron star. It's the densest matter in the universe. If you keep adding mass to it, eventually it will collapse under its own weight to form a black hole. So those are the densest objects, but neutron stars are still a form of matter. If you then have 2 neutron stars, you can think about a distance of about 30 miles. And 30 miles from me is LIGO. This is the Laser Interferometer Gravitational Wave Observatory. This one in particular is the single most sensitive ruler ever built. If you used it to measure the distance from us to the sun, it could measure that with a precision less than the width of a human hair. These things are really incredible machines. They were designed to detect gravitational waves, the ripples in the fabric of space-time itself. And that is interesting for short gamma ray bursts, because when you have 2 neutron stars orbiting each other, being here about 150 kilometers apart, they release energy as gravitational waves, causing them to move towards each other until they merge and explode. And a lot of things happen, which I will explain in just a moment. But you can see the orange that has come out, these jets that move outwards at basically the speed of light, powering what's shown in magenta, the short gamma ray bursts, these kind of sharp spikes and light curves that I've showed you. Those come just behind the emission of gravitational waves, which LIGO can detect. In the center here, this much smaller object is what's called a kilonova. The neutron stars get disrupted. These free neutrons merge with each other and form the heaviest elements, uranium, platinum, gold, and they are radioactive. When they're first formed, they release their energy into this plasma, which is heating the plasma, which gives you kind of a thermal transient that you can see in ultraviolet, optical, and infrared light at much lower energies than in gamma rays. I think sound will work. I'm not certain. Let's find out. But we know that this is what is occurring because of an event 6 years ago. This is the actual gravitational wave in spiral sound, and followed by a gamma ray burst. So 2 neutron stars merged 140 million light years away. They arrived at Earth within 2 seconds of each other. These signals were independently detected by LIGO. In this case, the image is showing the one in Washington, and the Fermi spacecraft, which is in orbit around Earth. We told the rest of the astronomy community what had occurred, and they went after it, and they found this. This little red dot right here is a zoom in this image and showing it evolve over time, is that kilonova signature. And it's outside of its host galaxy here. So you can see that it was born here. To form a neutron star, you explode a star. That explosion kicks the neutron stars out of their Milky Way, and 1 billion years or so later, they will eventually merge. So these are short gamma ray bursts. We can detect these now with light and gravity, but the brighter ones are called long gamma ray bursts. These have a different origin. So when massive stars are near the end of their life, they grow very large, and they get so large that they start shedding their own material to the surrounding area. And they'll do this for tens or hundreds of thousands of years, building up this massive nebula. In the center of that nebula is the star. Eventually, its core will collapse and form into a black hole. If it's rotating fast enough, it will drive these jets. First, they go slowly, but then they rapidly accelerate out to the speed of light. And if they're pointing at Earth, we will see them as extremely bright events. So long gamma ray bursts, they last more than 2 seconds. Again, you have these bursts of gamma rays with the brightness shown as a count rate over time. So this is an important burst detected by Fermi. And I'm going to step you through a series of them. Each of these bursts is about 10 times brighter than the last. Each one is pretty well known in my field. They all taught us something new. In 55 years of observing, this one was the record holder for total energy at Earth. And last year, this is what we saw. And it's actually a little bit hard to see, but this little blip here is actually the beginning of this large event. It lasts for about 10 minutes. And we realized that this kind of cutoff flattening at the top was a result of our detectors being unable to read out all of the photons. As Lynn said, it saturated our viewing detectors. A graduate student named Stephen Lesage did some really remarkable work to correct for that effect and reverse engineer the actual brightness of the event, which looks like this. So now in comparison to the other ones, in half a century of observing, this was the previous record holder. This little blip would have beaten this, but this thing is just an absolute monster compared to everything else we have ever seen before. In fact, it's so bright that it was detected by instruments never designed to see it. The first one being Voyager 1, a full day before it was detected by any other instrument. It swept through the solar system, first past Gaia, and then Integral. These are all a bunch of satellites owned by NASA, ESA, and other countries. It swept by Earth, and you can see the light up of Earth itself, which I will come back to in a moment. It swept by us, past the Wind and the ACE satellites, and ultimately the last detections occurring with satellites orbiting Mars. So one of the first questions we had was, how does this compare to other events? So you can see a measurement of brightness. This is a log scale, so each step here is a factor of 10 brighter. And you can see how many gamma ray bursts we've seen for fainter bursts and then up to brighter bursts over 50 years of observing. With that, we can overlay how often we see bursts of a given brightness. And you can see that, as you may expect, we've seen a few events on the order of once per decade. Previously, we had not seen anything in the order of 1 in 100 years. But we can extrapolate this out. 1 in 1,000 years and 1 in 10,000 years. So the end result of this calculation is that this burst was so bright, it's probably the most energetic one to hit Earth since recorded history began. Now, we didn't have gamma ray burst monitors, so we can't be certain, But we are sure that we were all particularly lucky to see this event. From this, we had observations from, I think, 160 telescopes. About 30 or 40 of those were in space. We've learned really a great deal about these sources, but I just wanted to pick one to kind of show you, which I think results in probably the coolest image we have of this event. This is not from the event. I took these while I was at the conference where we announced this. But if you are outside and the atmosphere has the correct conditions, you can see the sun and you will see around it a ring. And what happens is there's the direct path of the sun to you, but light can be slightly off and bent by water in the atmosphere and reflect down till you see it. And it has a fixed angle, so you end up seeing that as a ring all the way around you. On the right is the same thing occurring at night, this one being from the moon. And we saw something quite similar with this event, except instead of being invisible light that we can see, this was in X-rays. We ended up seeing in total 20 different rings. And not only did we see the rings, but they expand in time. So each individual ring is moving outwards, getting larger, measured over about the 2 weeks after this event. We do understand what's occurring. In the center is the aftermath of the explosion. The surrounding rings is light from the initial explosion itself. So on the right, we have a source. In between, in the orange and the yellow, are representations for clouds of dust in between us and the source. So the explosion happens, it propagates out. As the light hits these dust clouds, the dust will reflect some of the light back towards Earth. Each cloud will do this. And with the fixed angle for viewing, each cloud produces one ring. And as time goes on, those rings expand, corresponding to a greater angle. This effect is geometric. So when we observe these rings, we expand how quickly they grow in angular size over time. It allows us to map out how far away the dust clouds are that cause these rings to occur. And you can see a representation here of the Milky Way. We're here. This burst was aligned with the Milky Way. In each of these darker regions is one of the major dust clouds that correspond to the rings that we see here in X-rays. The furthest one is 60,000 light years away. And if you look on top, so now it's looking at, instead of face on, the Milky Way edge on. At that distance, the line, the path of where the X-rays came in is 5,000 light years above the Milky Way. And this was particularly surprising because the Milky Way should be narrower than about 1,000 light years out there. So we've learned that our own Milky Way is much wider than anyone thought. And we were never able to make this measurement before because we didn't have a backlight to show us this. So with a 1 in 10,000 year event, we were able to learn something new about our own host galaxy. That was great for X-rays. That was particularly frustrating for optical telescopes. This on the left is the Hubble image, and that little circle here is showing where the event came from. So a very crowded star field full of stars that were quite confusing. And on the right is the James Webb image, which allowed us to peer deeper, to look through the Milky Way, allowing us to actually see the host galaxy using the joint power of Hubble and James Webb. So the optical people were not quite so happy, but the rest of us really enjoyed this event. We announced the event in mid-March, and just about a week beforehand, when what appears to be pure chance, the second brightest burst seen in 55 years of observing arrived at Earth. And that light curve is on the left. Again, you can see time and count rate, and you can see that it's just about a minute or so long. So it's very solidly in the long class. We identified this quickly. We called up our colleagues. We got them to point telescopes to find the supernova. So short gamma ray bursts result in fainter kilonova. Long gamma ray bursts, you have a star, the jets blast through it and they blow the whole star apart. So weeks and months later, you'll see a supernova explosion. And we were then particularly surprised when we didn't see this. Instead, we ended up seeing, using James Webb, a particularly red source that looks kind of like a kilonova, which was very surprising because kilonova follow short gamma ray bursts, not long ones. And additionally, there's this host galaxy that's quite nearby in angular separation. So again, you have two neutron stars that form in this host galaxy. They form from the explosion of another supernova that kicks these out of their system, and they spiral outwards for 1 billion years before merging and creating this event. This was particularly surprising, but we were very lucky to get this. And we had been waiting to take measurements of a kilonova using James Webb. The reason is that the kilonova, it's powered by heat, so it's cooling over time. It cools past optical and into infrared, which is where James Webb was designed to look. And James Webb took this spectrum of the source, a measurement of the light as a function of energy. And people have waited to take this spectrum for 10 years. And we got this measurement. We have a model that we can compare to the Webb data. So the orange is our model, compared with these lines being the actual observation. And what we were looking for was a set of lines. In this case, we found a line complex. It's a signature of emission from tellurium. And tellurium is interesting because it's a particularly heavy element. So this is the first direct proof of where heavy elements come from, that indeed they are forged in the deaths of two neutron stars. So gold and platinum come from this. It's interesting for us to be certain about this because it does, from seeing how far they occur outside of their galaxies, it tells us this process takes 1 to a few billion years. And you need things like uranium with a long-lived radioactive half-life to keep the cores of planets hot for billions of years, to make sure you have a dynamo effect to power magnetic fields to protect the planet in the atmosphere from the effects of its own sun. So if you want to evolve complex life, you need heavy elements. And this measurement tells us that you couldn't have done that for the first few billion years of the universe. And we're pretty happy with this. We're very lucky to see both of these. I think we were very surprised to see them within just a few months of each other. And I have one more slide, which is the question I think I get most often, which is what happens if a gamma ray burst hits us. This is an artist rendition, so don't worry about it. If a gamma ray burst did hit us, it would be much larger than Earth, which I think is actually more scary. But it's just not something that's going to occur in your lifetime or any time for the next several 100 million years. So I'll stop here. I'm happy to take questions. It looks like there's some discussions in chat. So I'll read that, or raise your hands, or I'll let maybe Lynn or Ariana walk us through questions.
Yeah, well, I've answered a few of them, but we'll save this one for you from Dash. How does the heat affect gamma ray bursts or star explosions? I'm not sure which heat he's talking about, but maybe he means the temperature of the star, or not sure.
Dash, are you asking about those, or are you asking for like the reactions that occur in kilonova?
And Dash, it's okay to turn to answer verbally if you'd like.
Yeah, that's what I was asking about.
The nuclear reactions?
Yeah, does it affect the speed or the physical effects?
Yeah, it's a good question. It's a more specific question than I expected. So it's all of the forging of nuclear material occurs in about 3 seconds. So you have the two neutron stars. When they're merging, they're moving at about 1/3 of the speed of light, and it rips the material off. And it's a bit like nuclear popcorn. When you break off the surface, the crushing gravity is gone, so it just explodes out. And it's during that explosion that you get the neutrons kind of reacting with each other. If it's too hot, it will, you can get like a neutron to stick to a proton. And if it's too hot, they'll get disrupted and break off again. But it will cool quick enough that all of these elements get forged in about 3 seconds. And then they'll decay over the subsequent weeks and months and sometimes years, powering this transient that we get to see.
Oh, this is a good question. I'll let you answer this one too, since it just came in. Can you see it?
Yeah, I have it up. So Liam's asking, would the merging of neutron stars create elements that we have only been able to make synthetically? Yeah, so the things, I think it's technetium that doesn't have a long enough half-life for it to be around us naturally. They do get created in neutron star mergers, but then they rapidly decay away from being that element into other ones. So all of the elements that we have been able to create in laboratories get created in neutron star mergers, and elements that we have not been able to make and will not be able to make for the next probably 20 years also get forged in neutron star mergers. So we're hoping we get to the point where we understand these events well enough that we can start to learn about nuclear physics from them.
I think it's important to mention that pretty much all the, and you probably already mentioned that all the elements that are heavier than iron, I think, get made from the neutron stars, or at least we have evidence that at least half of all of them came from merging neutron stars.
Yeah,
I'm not sure we're up to 100% of them, but at least half of those heavy elements, gold, platinum, things like that are still around. That's where they come from. They're not made in the centers of regular stars because the regular stars can only make up to iron on the periodic table. So thank goodness for merging neutron stars, or we wouldn't have most of the stuff that we for technology.
so like Liam has another question. Could there be a way to measure what is given off in these events to identify new elements we don't know exist?
Good question.
I really wish we could, but I think, okay, it's technically feasible. I don't think it's going to happen for a long time, but when you form these radioactive elements and the atoms are so heavy, so the really heavy ones are the ones that we haven't created, they split through fission and they will release gamma rays. We do have telescopes which are designed, they're like nuclear telescopes. They look for those specific line signatures, gamma rays at the energies corresponding to the breaking of atoms. And it's feasible that if one of these occurred and we pointed a telescope quickly enough, that you could identify lines that we had never seen before and use that to understand what sort of nuclei could create them. But I don't think we'll be able to create a sufficiently good telescope like that for a very long time. I would love to do it, but I don't think I'll get enough money.
Okay, well, that's probably a good place to wrap things up and go back to Ariana to close this out.
Thank you.
Yeah, thank you for being here.
Thank you so much. That was just absolutely fascinating. I had seen the pictures of the rings and now I know where the rings come from, so I really appreciate that.